Recording. Okay, Bismillahirrahmanirrahim and good morning, everyone. So today we're going to start with a new topic, which is still under the organic chemistry. It's topic 15. It's another functional group called the halogenoalkanes, sometimes called haloalkanes. Okay. Other names for halogenoalkanes, as I have mentioned, is haloalkanes, or you will see that sometimes they are also called as alkyl halides. Okay, so halogens are your group 17 elements. Your fluorine, chlorine, bromine, iodine. So one way to easily spot your halogenoalkanes is when you have one of these halogens in a molecule. Basically, it is your alkane with one or more hydrogen atoms being replaced with halogens. So you can have more than one type of halogens in a molecule. For example, you can have chlorine and fluorine in the same molecule. And you can even have all the hydrogens being substituted or being replaced with halogens. In terms of naming, halogens are named as prefixed. So pre means it comes before the principal chain. So as you can see, when we name halogenoalkanes that contains fluorine, we call it fluoroalkanes. So more specific naming depends on the number of carbon atoms in the principal chain. Okay, so fluoro for fluorine, chloro for chlorine, bromo for bromine, and iodo for iodine. Okay, if we just recall back on how to name them, your principal chain will be the longest carbon atoms, continuous carbon atoms. So in this case, we have 3 carbon atoms, so it's called propane, and your halogen is on the side chain, bromo, and you need to number your carbon atoms and take the smallest number. So counting your carbon atoms can start from the left or from the right. It all depends on which one will give you the smaller number for the side chains. Next one. Sorry. Your principal chain would be the one with 4 carbon atoms. So we call it butane. And of the principal chain, there are 2 side chains hanging. This is your methyl group. And there's also your chloro. And they're both in position number, carbon number 2. So you call them 2-chloro, 2-methyl-butane. Why does chloro come first before methyl? Is because of the alphabet. Okay, C comes first before M. All right, so that's just a little bit of recalling on how to name your halogenoalkanes. Your first learning objective is to classify the halogenoalkanes into primary, secondary, and tertiary, the same way you have classified your carbocations. If you remember your carbocations from the previous topic, it is an intermediate in an electrophilic substitution of alkenes. Where you have primary, secondary, and tertiary, we use the same idea. Okay, so it depends on the number of alkyl groups. Alkyl groups are like your alkanes, but with 1 hydrogen less. Okay, so we want to first highlight your halogens and the carbon that is directly attached to it. So for the first example, where we have your primary halogenoalkanes, I am interested in the carbon-bromine bond, the carbon-halogen bond. Okay, so that carbon that is highlighted, I want to count how many alkyl groups that are directly attached to that carbon. So you can see that 2 of the bonds are attached to hydrogen, and 1 of them is attached to what looks like an alkyl group. It is an alkyl group, which is your ethyl. So in this case, we have one alkyl group, therefore it's called primary. So you can see the pattern already. If it's a secondary, again, highlight your carbon halogen bond. In this case, it's still CBr. And you want to look at the bonds that are directly attached to that carbon. So you have a methyl group, 1. That's just hydrogen on top. And on the right is also another methyl group. So you have 2 alkyl groups attached to the carbon that is directly attached to the halogen. Next, again, spot out your carbon halogen bond. And you want to look at the bonds that are directly attached to it. So you have a methyl, another methyl group. So that's already second. And the third one is your ethyl group. Okay, so this is why it's called a tertiary halogenoalkanes. So it works the same way, just like how you would classify your carbocation ions. It depends on the number of alkyl groups attached to it. Now, alkyl groups are sometimes represented as R group. So this is a summary of a primary, secondary, and tertiary. See hal, well, you don't see that hal often. Usually it is written as CX bond. A halogenoalkane is represented as a CX bond. Okay. Right. Moving on to the physical properties of halogenoalkanes. First and foremost, the functional group of a halogenoalkane is the carbon-halogen bond, which is most often represented by the CX bond. Okay, where X can be fluorine, carbon chlorine, carbon bromine. Okay, and if we talk about polarity, we go back to the idea of electronegativity. We know that fluorine is the most electronegative element in the periodic table. That gives fluorine the slightly negative charge, delta minus, okay? And your carbon will be delta plus. The reason for this is because there is a difference in electronegativity. Fluorine has a stronger pull towards the bonding electrons that are shared between carbon and fluorine. So the bonding electrons is not exactly in the middle, but it's much closer to the fluorine. That's the idea of electronegativity. Okay, compared to carbon chlorine, still chlorine is one of the most electronegative elements as well. It will have a delta minus, but not as big as your fluorine. Carbon will still become delta plus. Bromine, it will still be polar, but not as polar as the first two mentioned before, delta minus and delta plus. Now, carbon iodine is non-polar. The reason is because iodine has a very low electronegativity that it may be similar to your carbon. Okay, the value of electronegativity of iodine may be similar to carbon, so we treat them as nonpolar. Okay, now when we talk about polarity, we are essentially talking about the difference in electronegativity between the two atoms. Most common mistakes made by students is by when they add up the electronegativity values. Okay, you never add them up, you take the difference. Okay, so if we talk about polarity, we would CF bond would have the most polar bond, whereas CBr bond would be the least polar bond, and CI bond is just non-polar. Okay, the reason for this is because the value of F is really much bigger than carbon. So when you minus them or when you subtract them, they have a big difference as compared to bromine, which is not really that electronegative. And if you subtract the values of electronegativities of the two atoms here, carbon and bromine, the number wouldn't be that big. Okay, so this polarity depends on the difference in electronegativity values. Okay, so why do I want to talk about the polarity? Why carbon fluorine is more polar than carbon bromine? Because that will bring us to the next point. Okay, so just remember that in a halogenoalkane, even though there's carbon-carbon, carbon-hydrogen, non-polar bonds, there is a section of the halogenoalkanes that contains polar characters. It's usually on the carbon-halogen bond, the CX bond. The next physical properties that we want to look at is the boiling point. Just like other functional groups, alkanes, alkenes, the boiling points of these halogenoalkanes depend on the strength of the intermolecular forces. For alkanes and alkenes, we saw that the intermolecular forces was only ID-ID. But for halogenoalkanes, since there is a polar bond, there is an additional intermolecular force which is much stronger than your ID-ID, and it's called the permanent dipole. Okay, now I noticed that in your notes, it's printed as the van der Waals forces. Could you please change this van der Waals into instantaneous dipole, induced dipole, ID-ID? Okay, so I repeat again, if in your notes it is van der Waals, please change it. Thank you, Ayman. Okay, now that we know these two factors, these two intermolecular forces are present, the factors that affect the strength of intermolecular forces, which in turn will affect your boiling point, depends on the factors that affect the strength. Okay, so ID force, we know that there are two factors. The first one is number of electrons, which I think most of you should already remember by now. And the second one is the surface area of contact. Okay, that's for ID. If you want to talk about permanent dipole, it all depends on the polarity. Okay, so the more polar the bond, the CX bond, the stronger the PD. Okay, so again, how do we know this strength of polarity? It goes back to this concept. Okay, the carbon-fluorine bond is the most polar bond because the electronegativity difference is the biggest, and the carbon-bromine bond is the least polar bond because the electronegativity difference is the smallest. Next physical properties that we are going to look at is solubility. Same idea, polar loves polar, non-polar loves non-polar. Now, in the case of a halogenoalkane, for example, we have a fluorobutane. How do we determine if this molecule is polar or not? Well, there are two sides of the molecules. Okay, where your carbon-fluorine bond or carbon-halogen bond will be the polar side. So this polar side will be the one that is attracted to your polar solvents like water, for example. Ammonia is a polar solvent. Alcohol is also a polar solvent, usually the smaller chain alcohol. Okay? Carboxylic acid is also a polar solvent at the COOH, right? Whereas the other side of the molecule, usually called the hydrocarbon tails, because it contains carbon-carbon and carbon-hydrogen bonds, which are nonpolar. They are only attracted to, of course, nonpolar solvents. Okay, so nonpolar solvents are usually your organic solvent, like your octane, your nonane, all these alkanes with big number of carbon atoms in the molecule. Okay, so organic solvent, please take note, is usually nonpolar solvent. Okay, the idea of solubility is still the same for the other functional groups as well. So that's why sometimes we say that in general, the solubility of halogenoalkanes in water is only slightly soluble, because only this part of the molecule will interact with water. The other part will be water hating. This will be water loving, as we say it. So there's not a fixed rule to say if it's fully soluble or fully insoluble. It all depends on the structure. Okay, so that's the physical properties. Done. Your learning objective is more concerned with the chemical properties. So usually chemical properties depends on how they react, how they behave in a reaction, whether they react vigorously or whether they react gently, whether they react fast or slow, and etc. Okay. So describe and explain the different reactivities of halogenoalkanes with particular reference. If we look at the reaction of halogenoalkanes with aqueous silver nitrate. Okay, so before we look at the reaction of halogenoalkanes with aqueous silver nitrates, I want to talk about bond energy first. So bond energy is like the measure of the bond strength. Okay, the definition is given to you there, the amount of energy required to break 1 mole. Okay, so why do we talk about bond energy when we talk about the reactivity? In a reaction, right, in order for the reaction to proceed, you need to break a bond first, and then you form a new bond. Okay, so I'm going to use one example, just a simple example, which is a iodoethane. Okay, and then reacting with a hydroxy nucleophile. So what happens in this reaction is halogenoalkanes undergo substitution. The hydroxy will replace the iodine in the original halogenoalkanes. So I think you can sort of predict what product will be formed. When your OH is attached to that carbon, it becomes an alcohol, and your other product would be your iodide ion. Okay, so in order for hydroxy to kick out iodine in the halogenoalkane, you must first break this carbon iodine bond. So that is why I talked about the bond energy of your carbon, the bond energy of your CX bond, whether it's carbon iodine, carbon fluorine, carbon bromine, carbon chlorine. Okay, because it all depends on how easy or how difficult it is to break this bond. Right, the idea of bond energy, the higher the bond energy, that means the stronger the bond is, the more difficult it is to break. Okay, the bond energy values are given in your data booklet. Carbon chlorine bond is 340, carbon bromine bond is 280, and carbon iodine bond is 240. So as you go down, going from chlorine to iodine, you will notice that the bond energy is getting smaller. That means the strength of the bond is getting weaker. So we need to explain this. Okay, so let's just fill this in first. 340, 280, 240. And the bond energy for carbon-fluorine bond is somehow missing from your, not missing, I think they've decided to remove it for the reason because your carbon-fluorine bond is super strong that it may not even be broken. Okay, so the value is 467. So that's really high compared to carbon iodine. Okay, so explanation. Down the group, the halogen gets bigger. So the bonding electrons get more distance. More distant, sorry. So you have a fluorine with 2 shells, okay, and the positive charge nucleus is in the center, and you have your carbon there, and that is your bonding electron. As compared to iodine, where you have 5 shells, 1, 2, 3, 4, okay, you get the idea that iodine is big, and then your carbon is still the same size. Okay, so if you look at the distance between the nucleus and the bonding electrons is further in carbon iodine bond compared to carbon fluorine bond. So why does this distance matter? It is the attraction between the nucleus and the bonding electrons that holds the covalent bond. If you go back to the definition of covalent bond, it is the attractive forces between the nucleus and the bonding electrons, the shared electrons. Okay, so you can imagine the closer the distance is, the stronger the attraction. The further the distance is, the weaker the attraction. Okay, so that explains why, as you go down, carbon iodine is weakest compared to carbon fluorine. The halogen, the atomic size of the halogen gets bigger. The distance of the bonding electrons and the nucleus gets further. Therefore, the bond gets weaker. So that's the explanation. Okay, we will cover again this when we do topic 17, no, group 17. I don't remember the topic number, but it's group 17 where we will be looking at these halogens. On the next page, okay, well, it's still the same page for you, sorry. During substitution reactions, the carbon halogen CX bond will be broken heterolytically as follows. Okay, so you can see here during a substitution reaction, the carbon halogen bond will be broken down heterolytically. Okay, so we will only see that when we do the mechanism later on. Heterolytically means they break and move a pair of electrons at a time. Whereas homolytically is when you break the bond, you are only moving one electron at a time. Okay, so during substitution reactions, the carbon halogen CX bond will be broken heterolytically as follows. The carbon iodine bond will require the least energy to be broken, whereas the carbon fluorine bond will require the most energy to be broken. Okay, this is because of the strength of the bond. All right, so the summary of what I want you to get out of this is that the weakest bond will be the easiest to break, therefore the fastest the reaction. And so, because carbon iodine bond is the weakest, we say that iodoalkanes, that means any molecule that contains iodine, will be the most reactive. So if you have a choice between carbon iodine, carbon fluorine, carbon chlorine, carbon bromine, you carry out the reaction separately using the same setup, you will see that the iodoalkanes, the molecules with iodine, will be the fastest reaction. Now, how are we going to monitor this reaction? How do we know if a reaction is complete? Okay, we can't just, we need some observation. Usually we look at something that can be observed by our visible eyes in terms of numbers, in terms of volume of gas, in terms of reactivity, effervescence. But again, effervescence is not a good indication because we don't know if it's if it has stopped or it's just stuck, and we cannot quantify from just observing the bubbles. Okay, so that brings us to the next one, which I will not cover today because we only have less than 10 minutes left. And I think it's a good place to stop because this is the same place where I stopped with my block 4 as well. So the next section that I'm going to look at in the next lesson is by using aqueous silver nitrate to monitor the speed of the reaction, the rate of the reaction between iodoalkane, bromoalkane, chloroalkanes, and fluoroalkanes, if there is any reaction, okay? But it seems like fluoroalkanes, they have omitted the value for the carbon fluorine, so maybe it's not something that they want us to focus on, okay? So I will explain to you in the next session why we use silver nitrate. That's actually a hint. It's something that you have covered in your practical already. Okay, the silver nitrate is an important reagent to be used with your halogens or your halide ions, more importantly. All right, so that is all for today. Do you have any